Hello, hi Venkatesh.
Hello, sir. How are you, sir?
I'm fine. What about you? Happy New
Yeah,
Year.
fine, sir. Thank you, sir.
Yeah. Happy New Year.
Same to you, sir. All the best.
So we have to decide for April, right? I have spoken to Ambores. He is willing to give April or May, so that we can send some invitation to him. I'll write to you later. Yeah.
Yes, yes, sir. Yes.
Hello, good afternoon.
Yeah, good afternoon, sir.
Hi, Kanishka.
Hi, Anindra. How are you?
Yeah, good.
Yeah.
Good afternoon. Good to see you. Happy New Year, Kanishka.
Happy New Year.
Happy New
Yes.
Year. So maybe you can share your screen, Kanishka, and just check everything is okay. Yeah.
Shall I share my screen or
Yeah, you can share. Yeah.
is it visible?
Yes, it is visible. Yeah.
Just a moment.
Yeah, you can make it full screen, Kanishka. Let's see whether everything is okay. Yeah. Yeah. So yeah, good. So we'll wait for maybe.
Okay. Okay. Yeah.
But yeah, one can try. I mean, if Karnataka government is willing to do, we can. Maybe then it has to be arranged on a weekend or something, and
Right.
then bring people here and.
Probably once in a month, something like that, they can arrange.
Yeah, right. So they can arrange, and maybe they can arrange some transport or something like that. Can be
Right.
done.
Means earlier it used to happen offline only because I have given once this talk.
No,
This
that is in Bangalore Nano.
not Nano, Bangalore Nano. I have given. Then also in there is a setup of Karnataka government inside a GKBK campus.
Right.
So
So
the
that
big
is your
auditorium
thing.
I have
Right.
given once talk.
Okay.
Yeah.
So how is everything, Kanishka, at JNC sir?
Yeah, it's normal. It's nothing like nothing is like out of the line. So
So how is the funding situation?
sorry.
Funding situation.
Funding situation is not really great. Okay, so it was not like earlier.
Yeah. But you have lots of industry collaboration, right? Because you do
Not lot,
practical
only one industry.
only one industry. I see. Yeah. Okay. But DST nano mission and all gone, right? There is
Right.
no
Yeah,
there is no call.
No.
So in fact, you remember there is a last under thematic call. We had a project together, almost like 16 PI echo, I mean faculties from here,
Right.
and that money never came.
Yeah, our thing got rejected there. I was also a PI for her from JNCC.
Oh, I see.
Yeah.
Okay. So, for us, PSA was there, even Anil and all, everybody was there.
Yeah.
It was sanctioned like 2020,
Right.
or maybe 21, early 20, no, 20, I guess, 20.
20, I
Yeah, 20 before COVID.
yeah.
And never came money.
Yeah.
Yeah. And then nowadays, what is happening is, running lab is maintaining consumable is a nightmare, man.
Exactly. That's the problem we have.
And this CRG and all, whatever you write, they have a democratic boundary. Like,
Right, right.
so they have this number of divided by
Right.
denominator, and
Yeah.
So really suffering nowadays. Wait for maybe 1-2 minutes. People are just joining. I saw. Yeah. So Venkatesh, nowadays you have this online registration thing, or
Yeah, they do register, but they won't come, sir.
yeah.
Yeah, we do have, sir. We do have.
So this email, when you send for advertisement, like throughout the Karnataka, or there are some
No,
selected
we
places?
sent outside also. All
Outside.
Nano people who have registered,
Uh-huh.
our Nano conference, we send actually many actually. Sir. In thousands, we send actually.
I see. I see. Okay, maybe we can. People are joining because for the. Yeah.
Can we wait for a few minutes, sir? 2 3
Yes,
minutes?
You want to wait?
No,
Okay.
no,
fine, no problem.
Yeah,
No
just 2 3 minutes.
problem. Venkatesh,
Yes, sir.
I think we should proceed.
Yeah.
Sake of time, we should proceed.
Yeah. Yes, sir. Yes, sir. Thank you, sir. Okay. Good afternoon and welcome you all to the 6th talk of the Bangalore India Nano Webinar Series 2022-23. The Vision Group on Nanotechnology, Government of Karnataka, under the honorary chairmanship of Professor C.N.R. Rao, honorary President JNCSR, and the chairmanship of Navakant Bhatt, Dean Division of Interdisciplinary Sciences, and has initiated this webinar series. And this is the sixth of the series in this Nano Talk series. And today's guest speaker is Professor Kanishka Biswas, Professor at Jawaharlal Nehru Center for Advanced Scientific Research, Bengaluru. And topic of the proposed talk is the panoscopic approach towards ultra high performance thermoelectrics. I welcome you, sir.
Shall I start?
Yeah, now I request Professor Anindya Das, Associate Professor, Department of Physics, Indian Institute of Science, and also convener of Bengaluru India Nano Monthly Webinar Series to introduce the honorable speaker. Thank you, sir.
Yeah, thank you, Venkatesh, and thank you, Kanishka, for agreeing to give this, webinar to our younger generation. And it's my immense pleasure to, to introduce Professor Kanishka Biswas, and he doesn't need any formal introduction. He is very well known internationally right now. And Kanishka, so let me just briefly mention about his biodata as well as his achievement. So Kanishka obtained his PhD. He was an integrated PhD student from Indian Institute of Science. He finished his PhD program 2009, and followed by he did his postdoc from Northwestern University in 2012. And since then, he has been in JNCSIR, and currently he's a professor there. So he is working in various field of emerging area like perovskite halides to topological quantum material, 2D material, and of course the topic is this energy related issue, the thermoelectric energy related material. And he has published around 200 papers. His citations are more than 17,000. He is recipient of all prestigious awards of the country as well as international awards. So to name few of them, so he is recipient of Santi Swarup Bhatnagar Prize in 2021. He is fellow of Indian Academy of Science. He is invited fellow of Royal Society of Chemistry, London. He is recipient of Material Science Annual Prize, MRSI. So I don't want to go this in details. He's also recipient of Sarno Jayanti Fellowship and so on and so forth. He is also editor, executive editor of ACS, Applied Energy Materials, advisory board of several editorial board, as well as many committees and so on. So with this, I will not take time. I think we are looking forward to this talk. How to the today's title of the talk, the panoscopic approach towards ultra high performance thermoelectrics. Kanishka, yeah.
Yeah, thank you, Professor Das, for your elaborated introduction. But you missed one thing. He forgot to tell that we know each other from our PhD days.
Yeah.
Okay, so in IS. So with that, I thank Professor Das for his invitation, and also the organizer for this symposium, not symposium, like a talk series. Who were responsible for this invitation. I thank all of them. So today I'm going to talk about the panoscopic approach towards high performance thermoelectrics. So thermoelectric effect, just a moment. Thermoelectric effect is a direct conversion of temperature difference to electric voltage or vice versa. So it's divided in two effects. First one is Seebeck effect and second one is Peltier effect. So, and this Seebeck effect is discovered actually exactly 200 years back. Okay, and if you have like temperature difference like hot end and the cold end, semiconductor like P and N type semiconductor, which are connected in electrical series but thermally parallel, they can actually generate voltage from the temperature difference. So you have to create a temperature difference. The semiconductor will generate a voltage. So this is called Seebeck effect. Whereas the Peltier effect, we provide externally this voltage, and this same semiconductor can create temperature difference, where this active cooling end can be used as a refrigeration. So these Peltier coolers are there in the market for last 40 years, and you can search in Google or YouTube. You can see there are many products based on Peltier coolers, and as I work in a scientific institution, like many instruments are having these Peltier coolers. Where we need a control cooling, we will have this Peltier cooler in some of the instruments. So, but today I'm going to talk mostly about the Seebeck. So you can ask me a question like why one should do research in thermoelectrics in this country also across the globe. So you can see this total energy consumption pie chart for India in 2019 and world in 2019. You can see we consume energy in terms of combustion of mainly coal and petroleum and natural gas. That is almost all over the world. It is true. And combustion of coal actually generates the electricity, especially in this country, because we have many NTPCs in different parts of India. Whereas combustion of petroleum and natural gas actually runs the transportation and industrial sector in this country. So, but imagine like we use only 65% of the total energy. Sorry, we only use only 35% of the total energy, but 65 to 75% goes as a heat in these combustion processes, like combustion of coal as well as combustion of natural gas or petroleum. So we use only 35%, but huge amount of energy waste as a heat in nature in every day. So how to tap some amount of this waste heat and convert back to useful form such as electricity. So now if I show the Seebeck coefficient diagram, device diagram, and this consider this waste heat end is the heat source in the hot end in the Seebeck coefficient, and whereas this low temperature end can be room temperature or some lower temperature than the waste heat end, and then we have this efficient material which are P and N type, so they can actually convert this waste heat to electricity by this Seebeck end. So that's why research in thermoelectrics is extremely important, not only in India, also across the globe. So because these thermoelectric materials and devices allow direct conversion between thermal energy or temperature difference to electrical energy, and it will have a significant role in future energy management. So I'm not telling that thermoelectric will solve all the problem, but it can actually couple with the other energy technologies where it will have a bigger role. So I'll give some example at the end of my talk. So you can see like the direct heat to electricity conversion in large scale. It can be used in power plants like chemical, thermal, nuclear, steel, any kind of power plant where we lose heat every day. Whereas in medium scale, it can be used in exhaust pipe of the high-end cars where this combustion of the fuel generates waste heat, and this can be converted to electricity, and which can actually charge a battery in the car. So we need a hybrid car, and actually BMW, Ford, GM, they have this high-end car which are based on this thermoelectric technology. And then now in last 45 years, NASA as well as Russian Space Foundation, they are using this thermoelectric technology to power their spacecraft for deep space mission. So as many college students are hopefully attending this talk, I'll elaborate this. For example, like if we go a deep space mission, like if you are sending the spacecraft to Mars, for example, do you think how the power or electronics of the spacecraft will be running so that we can get a photocopy? Because see, solar cell intensity will go down and down if you go far from sun, right? So Earth, if the solar cell is 10%, Mars will be less than 1%. So we cannot actually use solar cell to give power to the electronics for this deep space mission. So what actually NASA first they have done, they have created a radioisotope thermoelectric generator. For example, in a glass chamber, a sealed glass chamber, they put plutonium oxide. And plutonium half-life is 28 years. And it decays at least for 28 years and gives the heat of around 300 degrees. And this glass jar is actually covered by thermoelectric generator. So 28 years, this thermoelectric generator get a heat of say around 300 degrees, and they convert this heat to electricity, and they actually runs many electronics and camera, all this thing of this deep space mission. So this technology has been used in many missions of NASA. So this is one picture where they have used. So they have used actually for 11 to 12 missions, they have used this radioisotope thermoelectric generator. And this technology first has given the confidence to this scientific community. Actually, thermoelectric generator can be used for other things like large scale power plant or medium scale or several other things. So now the new users are coming. Is basically the solar thermoelectric. For example, like we know all solar cell, right? Which are actually very popular nowadays. So solar cell actually convert the light part of the solar to electricity. So now, if we consider the solar energy, there is also a heat part, right? So what to do with the heat part? So now if I combine solar cell with thermoelectric, it will be a very efficient system. So that's why these solar thermoelectrics are the new area of research. Now another example is basically when we have mobile phones and laptop, right? And we talk more in mobile phone or use laptop more, it heats up. If you talk half an hour in your mobile phone, it will heat up because our mobile phone has a lithium-ion battery, and our government actually going towards electrical mobility. So government says that in 25 to 30 years, all cars will be replaced by battery cars. So as soon as we replace by battery, it will have lithium-ion battery and it will heat up. So what do we do with this waste heat, right? So can we combine thermoelectric technology with this battery technology so that we can convert this waste heat from the battery and convert it to electricity? So that's why I said this thermoelectric will have a significant role in future energy management, but it has to go with other energy technology like such as solar cells as well as battery. So there is an immense huge one can have in this thermoelectric. So let's go to the fundamental science about this thermoelectrics. I talked about application, and the rest of my talk I will not talk about application. I will talk about fundamental science. So if you see this equation actually governs the thermoelectric performance in a material, which is nothing but ZT, which is thermoelectric figure of merit, which is purposefully made to be dimensionless, so that one material can be compared with another material easily, which is more efficient. So numerator of this ZT, we have Seebeck coefficient. Seebeck coefficient is nothing but how much voltage one material can generate unit temperature difference, which is delta V by delta T. And sigma is electrical conductivity, which is nothing but how electron and holes moves around a solid, how fast they can go, which is directly proportional to the carrier concentration and mobility of the system. So denominator is having thermal conductivity, and thermal conductivity has two parts. First part is the electrical part of the thermal conductivity, how charge carriers carry the heat in a solid. So this is directly related to the electrical conductivity by famous Weidemann-Franz law, where K electronic or K electrical is directly proportional to electrical conductivity of the material. So we don't have a direct control of this electrical part of the thermal conductivity while maintaining the high electrical conductivity of a thermoelectric material. And another part of the thermal conductivity is basically how phonon or lattice vibration actually carries the heat in a solid, which is the only independent part in this equation. So I'll show some of the strategies how we can modulate this lattice thermal conductivity, or we can make this lattice thermal conductivity lower and lower so that we can have high ZT. So I am a solid state chemist. I think this problem slightly different way. So we can we have to have a high electrical conductivity, so that we need a property of metal. We need to have a high Seebeck coefficient, which is a property of a semiconductor, and we have to have a high low thermal conductivity, as it is in the denominator. So we have to have a property of glass. So on thermoelectric materials should have metal, semiconductor, and glass property together, which is extremely challenging, where chemist has a very big role to play, because they can make new material by utilizing the concept of chemistry and chemical bonding, where actually we can implement metal-like or glass-like or semiconductor-like property in a single material, which is the grand challenge in this field. So we have to have a metal, semiconductor, and a glass in a same material to have a good thermoelectric. Okay, so if I say more scientific way, we have to actually have decoupling of electronic and thermal transport. So that means how we can decouple electron and phonon in a solid. So so it will be better thermoelectric. So what I mean that crudely, we have to decouple the numerator and the denominator to have a good thermoelectric property in a solid. So now this is lattice thermal conductivity. So lattice thermal conductivity, as I told you, is carried out by the quantized lattice vibration, which are nothing but the phonon. So phonons carry heat, and they have in the range of wavelength of 1 angstrom to 100 nanometer, for example, which actually carries the heat in a solid state metal tellurides or other important thermoelectric material. So there are two kinds of phonon. First one is acoustic phonon, which when all the atoms in a solid vibrates in same direction, which generates the acoustic phonon, which are nothing but the sound wave in a solid, and which actually carries the heat in the material. So we have to scatter this acoustic phonon. So another type of phonon is the optical phonon, where atom vibrates in different direction and creates dipole moments and polarizability. which calls the optical phonon, which can be tracked by different spectroscopic techniques such as Raman, IR, or terahertz spectroscopy. So we have to scatter this acoustic phonon to decrease thermal conductivity in a solid. So people have tried over the years how to scatter this acoustic phonon, and to be precise, these acoustic phonon wavelengths are generally in the 1 to 20 nanometer, which actually carries the heat in this class of thermoelectric, high performance thermoelectric material. So 1950s and 60s, people have tried to make solid solutions, like say making material like say lead tin telluride or lead telluride selenide. So they will dope selenium in tellurium position on tin on lead position, so that they create point defects or atomic point defects, which are very very short scale in the angstrom scale, which are not so important to scatter the important phonon, which are in the range of 1 to 20 nanometer. And they have done created grain boundaries, and which are in mesoscale, like micron scale, which are also not so important phonon, which carries the heat. So, for example, you see this lattice thermal conductivity versus temperature plot for lead telluride, which is a champion material. This is the high temperature plot for lead telluride, which is a champion material in this field. So as I told you, when you create this kind of solid solution or point defects, the thermal conductivity decreases, but it does not go to the amorphous limit or glass limit. Okay, so that created us like ZT of around 1 in this kind of material, which is known from 1960s or 70s by mostly by Russians and scientists from USA. So then these paper first in 2004, they showed that they have created this lead telluride sample with a nanodot embedded in this lead telluride, which are in the size of say 1 to 20 nanometer. So these nanodots are exactly the same size of the phonon mean free path, which actually carries the heat. So once they created this nanostructured bulk material, I would say this is not a nanoparticle, but nanoparticle embedded in a bulk material. So I say this is a nanostructured bulk material, which shows almost like a glass-like thermal conductivity, and which created a sensation, and which actually gives rise to a ZT of around 1.8 for the first time in lead telluride, and open the gate for nanostructured bulk thermoelectrics. Okay, so then several important papers came in this field. I have cited some of the few where people have created hierarchical architectures from atomic scale point defects to nanoscale precipitates to mesoscale grain boundaries. So they scattered all ranges of phonon and got a ZT above 2 for the first time in lead telluride, and I was involved in that kind of work during my postdoc. Then when I came back to India, I thought like, okay, so this extrinsic nanostructuring basically scatter phonon heavily, terribly decrease the thermal conductivity. But at the same time, like say this is a foreign elements, right? And once the lattice are completely mismatched, so the boundary of this precipitated matrix are having huge amount of dislocation and defects. So they actually scatters the electron and hole. So we always compromise with the numerator of the ZT, and we get a suboptimal ZT by this extrinsic nanostructuring approach. So can we think of a new approach where we see an enhancement of the electronic conductivity and decrease in the lattice thermal conductivity at the same time? So this grand challenge was there for this field for almost 10 to 15 years or around 15 years. So enhancement of the electronic transfer and reduction of the thermal conductivity at the same time. So in that direction, we are working almost 10-11 years when I started my group in JNCSR in 2012. So we started working this class of compound. So this is one class of compound we work from beginning of my lab. But of course, I work in different classes of compounds. That today we don't have much time to show other classes of compound. I'll give only one class of compound today. So this compound called 1562 compound, although it looks complex, I'll simplify. One is nothing but either sodium, copper, or silver. 5 is antimony or bismuth, and 6 is sulfur, selenium, or tellurium. So these compounds generally crystallize in the basic solid state chemistry structure, which is sodium chloride structure, which is interpreted in phase center cubic structure. So sodium sits in the octahedral hole as well as chloride sits in the octahedral. So now I'll talk about only one compound today, is AgSbTe2, which have this rock salt structure, where Ag and Sb actually disordered in the sodium position. So they are crystallographically confused. So they don't know their position, but they sit in the sodium position. They don't go to the chlorine position. So chlorine position is taken by the tellurium lattice, which is a static lattice. So this please note that the cation position, silver and antimony is disordered. Okay. So and this is not a new compound, AgSbT2. This was discovered again in 1980s. And there are several groups working this compound, and there are several experimental reports which actually claim that the silver and antimony is actually disordered in this position. And we have also synthesized our lab, and we showed by the crystallography silver and antimony actually disordered in this compound. Then from this group, from Bhanu Mohanty's group in Michigan State, they published a paper in PRL in 2007. They said that actually there are several ordered structures are possible if silver and antimony orders in the sodium position. So then it creates a supercell, and it will have not having the exactly sodium chloride structure, but it can have a cubic or tetragonal type of structure where silver and antimony is ordered. Okay, and we try to make this ordered structure from 2012-13, but we have not succeeded for many years. And you can ask me question why we are looking for this ordered structure, right? So to do that, we have to understand the concept of Anderson localization. So now, if we have more and more disordered in a lattice or any crystal structure, electrical conductivity will be decreasing, right? And in a critical level of disorder, the metal will become insulated. So that is called Anderson localization. And this can be understood by this schematic for students. So if we have valence band and the conduction band which are overlapping, so this is basically a semi-metal. So as soon as I have, like, for example, silver and antimony disorder, more and more disordered, which is actually true in this compound, we have localized states. Okay, and these localized states these are the localized states, and these localized states are separated from the extended states by mobility edge, which concept is given by Nevin, again, who got Nobel Prize with Anderson in 1917. So this mobility edge separates the extended states from the localized states. Now I have AgSbT2, which has silver and antimony intrinsically disordered. So I have a lot of this localized state in this compound, which is not good for thermoelectric, because if my Fermi level, which is nothing but how much the hole fills up or the electron fills up in the conduction band or valence band. So this Fermi level falls inside the mobility edge, their electrical conductivity vanishes. I have electrical insulator, which is no good for thermoelectric. So basically this Anderson localization is no good for thermoelectric. We have, but you see, if mobility edge moves towards Fermi level, we'll have a distortion in the density of states. Okay, so that goes away from a normal parabolic dependence, and that will have features like this. From this Mott equation, you can see Seebeck coefficient is directly proportional to the first derivative of the density of states at the Fermi level. So first derivative of the density of state is nothing but the slope, right? So if we can create a high slope at the Fermi level, basically we can have a jump in the Seebeck coefficient. That is called basically the resonance level. So if mobility edge moves this side, my electrical conductivity decreases, but Seebeck increases. So that means by tuning this mobility edge or tuning this order or disorder in this compound, I can play around with this electrical conductivity and Seebeck coefficient. That's the motivation we have. So as I told you, Anderson localized regime is no good for thermoelectric. We have to work in a regime which is a precursor of Anderson localization regime, which is nothing but a weak localization regime. So where we have a partial disorder of atom, and electron and hole actually will have a diffusive transport, and this regime is good because we will have a finite amount of electrical conductivity as well as some distortion in the electronic states where we have a good Seebeck coefficient. So we have to work in this weak localization. So basically we need to partially order this Ag and Hb. That's what we don't need complete ordering of Ag and Hb. So how to partially order an Ag and Hb? That we have tried with chemistry for a long time, and these two gentlemen, who is Shubhajit Roy Chaudhary, PhD student, and Tanmay Ghosh. Shubhajit was a chemist and Tanmay was a physicist. Both are not there in my group anymore. So Shubhajit is working as a Humboldt postdoc in Claudia Felser group, and Tanmay also works as a Humboldt postdoc in Wittig group. So they actually came up with the idea of how to make them partially ordered. So what they have discussed with me, they told that, okay, see, like silver and antimony, both are disordered in sodium salt. Okay, So let's try to understand why they are disordered. Okay, and in this class of compound, we will have say GSBACD that is also disordered. Like all these compounds are actually disordered and sodium side. So that is the beauty of this compound. Okay, so now silver is +1, which is the size of 115 picometer, and antimony is +3, which is 76 picometer. Now you forcefully put this dissimilar charge and dissimilar size to atom in the sodium position, which is octahedral position. So they don't like that position. So they don't fit in this position, and they jump each other and they become disorder. So that is the chemistry behind that. So their dissimilar charge and dissimilar size make them disorder. So how to make them order? So we try to dope in antimony and silver side many ions throughout the periodic table. Okay, so we ended up with cadmium. So you see, cadmium has exactly the average charge +2 of silver and antimony, and exactly the average size. So if you add 115 plus 76 divided by 2, it is equal to 95. Okay, so we came down to cadmium, and as soon as we dope cadmium, I'll tell you the story. Basically, silver and antimony gets partially ordered in this compound, and we have several proof to tell that. So I'll give the proof now. For example, like when you have done this powder X-ray diffraction, which is the like fingerprint experiment, to check this kind of order disorder or any kind of new changes are happening in the sample or not. So this is the X equal to 0 is basically pristine sample. So AgSbT2. So AgSbT2 always forms slightly non-stoichiometric in the phase diagram of Ag2T and Sbt2. So that's why it has always a Ag2T type of impurity, which is actually destroys the thermoelectric property of AgSbT2. But as soon as I dope cadmium, for example, 2 mole percent to 4 mole percent to 6 mole percent, this Ag2T peaks slowly goes away. You don't see them. So that means something new chemically happening in this sample. But as soon as I dope 8 mole percent of cadmium, you see there is a peak of cadmium tellurate comes up. So that tells that this system can take only 6 mole percent of cadmium. After that, the solid solution breaks and it goes to a phase separation of cadmium tellurate. So 8% sample is also no good. So we have to work in this regime of 2 to 4 mole percent of cadmium doping in this sample, which is very low percentage of doping. Okay. So now another way to think basically why we choose cadmium, because cadmium is 2+. We are doping cadmium in antimony position. So antimony is +3. Okay. So if I dope +2 in +3 position, it will create one extra hole, right? So once it creates extra hole, basically I dope hole in this system, my Fermi level goes away left side, right? So it actually moves away from the mobility stage. So we have an extended transport. So that way also we can think this +2 doping is good in this sample in place of antimony, not in place of silver. So that is a logical way of thinking of which doping element to choose actually to tune the Fermi level to mobility edge gap in this solid. So let's see what happened. So then we have measured the low temperature resistivity, which actually gives, which is the indicator of localization, delocalization in this kind of solid. For example, this is the AgSbT2. When you measure the low temperature resistivity, it shows a upturn and this kind of minima. And when this kind of minima comes, this gives direct signature of this localization. And by fitting this low temperature data, which actually gives rise to root 2 dependence, and basically which tells that this is nothing but the enhanced electron interaction, and the coherence destroys if we have more electron phonon coupling in this material. So this side we see a increase, and this minima temperature actually indicates how much disorder we have in this material. Okay, if the minima temperature shifts towards lower temperature, that means we have less disorder. So we have delocalization of electron states. We need delocalization, not localization. Okay, so this AgSbT2, which is intrinsically disordered, we see a minima at 60 Kelvin, 62 Kelvin. As soon as I dope 6 mole percent, we see the minima is in 11 or 12 Kelvin. So cadmium actually orders this silver and antimony partially and shifts the minima to low temperature, and you see a delocalization of the electron states. Now let's see what happens if we measure the low temperature Seebeck coefficient. Okay, and low temperature Seebeck coefficient, you see like this pristine sample, I have a bump in Seebeck coefficient, exactly same temperature where this minima comes. And this bump is nothing but the distortion of the density of states, as Mott predicted long time back. We see a jump in the Seebeck coefficient. As soon as I dope cadmium, the bumps goes away. So that means the mobility edge is going far away from the Fermi. Okay, so we have a delocalization of the electron state due to partial ordering of silver and antimony. So then we have measured the mobility, and this compound is semi-metallic. It has both hole and electron, but hole concentration is much more, is around 10 to the power 1 into 10 to the power 19, while the electron concentration is 17. So this is hole dope sample, as I told you, cadmium 2 plus dope in the antimony position. Okay. So now, as soon as I dope cadmium, the whole concentration doubles in this sample, but the mobility remains same in the low temperature region, even in room temperature region. So that means the mobility, we don't see a decrease, although the whole concentration double. That happens due to basically delocalization of the electronic state. That also tells that, and this delocalization actually enhances the electronic transport in this material. Okay. So now we have collaborated with our theoretician colleague, who is nothing but Professor Umesh Bagmani in our institute, who showed that by formation energy calculation, the ordered AgSb-T2 is lower order, lower energy structure than first nearest neighbor and second nearest neighbor structure, which is predicted by Mohanty in 2007 in his PRI. So as soon as we dope cadmium, actually cadmium doped ordered structure has even much more stable structure. So that's the indication. There are a lot of information from this plot. I have no time to tell in details. So then he has calculated the electronic structure. This is the ordered AgSb-T2. It has nearly dispersed valence band and conduction band, which are overlapped at 0 Kelvin. So it is basically a semi-metal, as I showed you from the schematic. So when we make, like say, disordered AgSb-T2, theoretically, you can see there is a nearly dispersed, like localized states are coming at the Fermi. So that's what this is the mobility edge, what we predicted intuitively from our experiment. Okay, so this is the localized state, which is nothing but the tellurium p orbital. So tellurium p orbital is completely localized at the Fermi level when you create this disordered AgSb-T2. Let's see, this is the disordered AgSb-T2 localized states. As soon as I dope cadmium, Fermi level goes down and localized state vanishes. So that tells that basically Fermi level takes away the system from the mobility edge, and also it breaks the localized states due to partial ordering of Ag and Sb in this material. So then you can ask me a question. Okay, so you have done like electronic transport at low temperature, Seebeck coefficient, theoretical calculation to show that okay, we have some indication of partial atomic ordering. Can I see by eye? Okay, so to do that, we have done high resolution HRSTM study, a head-up study. You can see this is the pristine AgSb-T2. And this is the 1-1 plane of AgSb-T2, which is nothing but the silver and antimony plane. So you only see silver and antimony in this plane. But we don't see any kind of ordering. Silver and antimony completely disordered. Now, if I do more crystallography in this, is the electron diffraction spot from this region. You can see the fundamental spots are due to the sodium chloride structure, the disordered structure. We don't see any superstructure spot, because once we have a superstructure, that is the indication of ordering, which actually can create supercells, right, in this compound. Then we have done for cadmium AgSb-T2. You can see there is an intensity distribution inside this circle, and the circle size is basically 2 to 4 nanometer, which actually forms endotaxial type nanoscale superstructures. Okay, which by cadmium ordering, cadmium dope silver and antimony ordering in a very local scale. So this is not a global scale ordering which we wanted. And electron diffraction or crystallographic tell you the yellow arrow you can see. I don't know if it's visible in these slides or not properly to the audience, but you can see very, very weak halfway spots. The halfway spots means basically there is a cell doubling is happening. As soon as I dope cadmium, silver and antimony is ordered in this compound, and cell doubling is happening, and cell doubling is creating this ordering. And when we have done more image analysis by inverse fast Fourier transform image of this, by only selecting this superstructure spot, you can see clear domains of atomic ordering in this compound, which is the size of 2 to 4 nanometer. Now, previous phonon calculation in this compound AgSb-T2 tells that the phonon mean frequency in this compound is the order of 1 to 10 nanometer, or rather I could say specifically 1 to 6 nanometer. So these ordered domains will scatter hugely the acoustic phonon in this compound, and it will decrease the thermal conductivity. While also enhancing the electronic transport by delocalization of electronic state. So by we have two handle in this compound. By doping cadmium, it orders the atom in a domain size of 2 to 4 nanometer, which is exactly size of the phonon, which is the message I wanted to give you. So then we have keep on doing more TM analysis. You can see these ordered domains and more electron diffraction. I'm not going to bore you more with this. Then we see not only this halfway spot, we see a superstructure spot, very nearby spot. So that tells that basically nanoscale superstructures, okay, in this compound. So then more careful TM analysis shows that we have ripple-like structures. Okay, so this is called strain ripple, which is observed in many materials in metallurgy. Okay, metallurgy field. So these strain ripples are nothing but telling that these materials are highly strained. So these strains are also good to actually decrease the thermal conductivity. So where from the strain ripples are coming? So now, if you remember the slide where Mohanty proposed, this ordering can happen in different directions, right? In this compound. So now this will create similar energy or similar lower energy structure, ordered structure, which will be sitting in different local minima of energy diagram. Because ordering can happen in cell doubling or cell tripling or many other ways. Okay, but those will have like similar lattice parameter. Once we have similar lattice parameter, similar energy structure, so compound can go and sit in different kinetic minima or low energy minima, right? So once it happens, it will create huge strain in the lattice. Okay, and that's what we are seeing in that TM, and that tells that basically this ordering of atom actually creates this strain in the lattice, and that is very good to decrease the thermal conductivity. So with that, we have measured the low temperature heat capacity to identify what is happening more in this system. And low temperature heat capacity is an indicator of many things. One thing I'll tell here: low temperature heat capacity data we cannot fit by simple Debye model. So Debye model is this is Cp by T versus T square. So if I take this T this side, so this is really D by T cube, right? So that we read in the class in BSc. So this cannot be fitted by simple Debye law. So we have to have Einstein modes. Actually 3 Einstein modes to fit this heat capacity data. So what are those Einstein modes? These Einstein modes are basically the low energy phonon modes, which are generated actually near basically this cadmium doping in this sample. And this low energy phonon mode tells that it has huge number of or high density of low energy optical phonons, which are also good to scatter acoustic phonons. Okay, and these are the you can see these low energy optical phonons are in the range of 27 to 105 Kelvin, and energy it's in few centimeter inverse only. And the Debye temperature we have estimated is only 160. So 160 Kelvin, all phonon modes are excited. So this is actually a very low thermal conductive material. And then when he plotted Cp by versus T cube with T, we see a boson-like T, which exactly tells that there is excess low energy optical phonon modes in this compound. So then we have measured the high temperature thermal conductivity, because that is the important thing to estimate the ZT at high temperature, which is actually can go to the application. So you can see the lattice thermal conductivity data. This is the pristine sample, which is flat at high temperature, because the phonon mean frequency it's very low in this material. It's around a few nanometers only, and that gives actually a glass-like transport, which is well known. But it decreases more as soon as I dope cadmium, because it has this nanoscale domains which have a huge amount of phonon scattering and give rise to this ultra low thermal conductivity, and it is to the glass limit of this material, 0.2 watt per meter Kelvin. But the surprise is that as soon as I dope cadmium, the electrical conductivity enhances. So this is the red sample, which is 6% cadmium dope. The electrical conductivity, which is quite good in this material, having this very low thermal conductivity. So we have like almost glass limit thermal conductivity, but very good electrical conductivity. That's what the motivation we had for the long time. And with that, we have estimated the ZT. And you can see the ZT at room temperature is around 1.6, which is one of the highest at room temperature. And it goes to around 2.6 at around 570 Kelvin. So this then I compared ZT with other material which are state-of-art material in the field of thermoelectric. You can see this mid-temperature range. This material actually outperforms all the materials which are discovered till now. Whereas high temperature, there are other materials like say SNSC that gives a ZT of 3, which is a Nature Material paper from Inchang group from Seoul recently. And but this is for high temperature application. But for mid temperature, this material is one of the highest. Not only published this paper in 2021, We have patented Indian patent as well as PCT and US patent based on this binder. Okay. So, can somebody mute?
Yeah, Venkatesh, is it possible to mute?
Anyway, so I'll continue. Okay. So then,
Arun, please mute that one.
yeah, sure. So no problem. Yeah. So okay. So then, based on our paper, exactly same year, another perspective came in science by Maria's group from Austria. So it was a quite sensation in thermoelectric, because thermoelectric field till now believed that disordering is good, because disordering scatters the phonon. But we said we actually swim across the web and said like disordering is no good. Little bit ordering is good, where we can have delocalization of the electronic state, and if the ordering size comes fortunately in the order of nanometer, some few nanometer, which is we can match the phonon mean to it, we can scatter also the phonon. So that's what is written in the perspective by Maria, and it was actually highlighted in several medias, from English to Kannada to Bengali, like all kind of media. It has highlighted this word. So with that, we went. How much time I have? Another 5 minutes.
Yeah, another 5 minutes definitely.
Sure. So I'll finish it in another 5-6 minutes. So we know the periodic table well as a chemist. So we tried doping other elements. For example, zinc, cadmium, mercury comes in a series in a periodic table. If you see the periodic table, if you have in your hand, you can check. So zinc size is 74. It does not work. It does not order the silver and antimony. But cadmium size is 95. It orders. And then we dope mercury. We see a shift of minimum. Okay, so there is a clear signature of ordering, because that size is also very close to the average size. And then we see the similar feature in the Seebeck coefficient. And we have collaborated with our Ranjan Datta here, who is expert in TEM. And you can see, we see clear signature of ordered nanodomains. This is much more clear than the last one. And we can see the cell doubling as well as superstructure spot, what we have seen in the cadmium. So we are writing this paper. And we measured a GT of 2.4. So basically, what we proposed in cadmium, that can be generalized in mercury, and ZT is also very high. So that actually generalizes our concept, whatever we have given in cadmium doping in this compound. So then what we have done, we have created a 4-leg device, and which gives very, very high power in this device, which gives the efficiency around 6 to 7%, which matches market-based material. So then we went ahead, we created silver vacancy in this compound. Okay, because silver creates lots of disorder in this compound. So we wanted to remove some of the disordered silver so that we can have a atomic ordering. So actually it creates much more better atomic ordering than cadmium doping. And this work has been done by my PhD student Riddhimay. And we have again collaborated with our TM collaborator Jaiching, who has a very good TM. And actually he showed this drop in the head of intensity that actually tells that silver goes away from the matrix. And this is the silver vacancy. The red one is the silver vacancy we are seeing by eye. Okay, and near the silver vacancy position, we see this atomic ordering, and which is the size again 2 to 4 nanometer. And we have done extensive TM to understand this vacancy dope atomic ordering, and this also gives rise to a GT of 2.3. And we have submitted this paper now for publication. And we have done much more detailed study in this. And so what we want to tell here, basically this atomic ordering or partial atomic ordering concept is a general one, and we have followed up with this. And there are several groups has actually published paper after we published our paper in Science 2021, which they supported our concept, and they also find it out by partial atomic ordering. Somebody can tune this mobility edge and enhance the thermoelectric transport. So with this, we have collaborated with Tata Steel last 4 years, because Tata Steel contacted us. Because Tata, like steel power plant, there are several sources of waste heat, and they contacted us, and based on our 4 patents, based on bismuth, antimony, tellurium, selenium material, because they wanted to actually convert the waste heat in the range of 105 to 110 degrees centigrade, not very high temperature. So this is a photograph from their steel power plant. You can see that there are several steam lines running through this power plant, and they actually quenches the blast furnaces, which actually melts the iron or steel. Okay, and they waste huge amount of energy. So we have generated material which actually works in this temperature range. And we have created a small video. So actually, like next week there will be a prototype demonstration in that steel power plant. Let's see. We have created a multiple link device. And this was first time in India. So this first time in India, which is going to put in the data stream power. Okay, so no need of like I have told you whatever. Yeah, so you can see this is my total team. These two guys have worked in the device. Thank you very much. So with that, I come to the conclusion. So today I showed we measured extremely high thermoelectric figure of merit in cadmium dope as well as mercury dope as well as vacancy dope AgSbTe2, which actually can be used for waste heat to electrical energy conversion in chemical, thermal, nuclear, or steel power plant, or also in automobile industry in households. And we showed here like atomic ordering can delocalize the electronic states and can enhance the electronic transport. At the same time, if the ordered nanostructure size is in the same size of the mean free path of the phonon, it will create a huge decrease in the lattice thermal conductivity. And the demonstrated strategy opens a new avenue in the field of thermoelectrics, as most of the thermoelectric material has an inherent disorder. With that, I acknowledge my group, I have excellent sets of masters, PhD, and students and postdocs who actually generates lots of new idea in my group, and I just discuss with them and give this kind of talk. Okay, so they do this job, and I have excellent collaborators. The purple colors are actually contributed in this work, and I have several other collaborators which actually we work together for different fields, and generous funding from ACRB, DST, Shekshaka Laboratory, Tata Steel, and JNCSR. And I would be happy to answer if there are any questions and discuss. Thank you very much.
Thank you, Kanishka, for a wonderful talk. Let's thank Professor Biswas for a wonderful talk. So now it's open for question, comments. Attendees can, unmute, and you can ask the question, or you can chat also in the chat box.
Some chat box, something is there.
Yeah, no, that's a comment. It's saying that
That's a comment from Kavita. Okay.
Kavita, yeah, Dr. Kavita. Yeah.
Sir, I have a question. How much electricity we can generate, and what instruments it can run?
Yeah, so this is a very, very good question. You know, like, you can see here, I'll show you a data. Okay.
Yeah, related to that, Kanishka, what you have made this prototype one, how much voltage does it generate?
Yeah,
for
so
what?
That is actually 3 watt. Okay.
Wow.
3 watt. So now you can see this is like a half a milliwatt. Okay. Half a watt. This is my own lab made device. Okay, 4 leg, half a watt. So that can generate if you give a temperature difference of around 300 degrees centigrade. Okay, so now what Dr. Shiva Prasanam from ARCI has done, so we have scaled up material, sent it to him. So that I have showed you that the circular disc that was 200 gram. Okay, and this device is around 10 gram. So that if we chop the leg from there, and we can get around 3 to 4 watt. Okay, and now if we can surround these pipes, like for example, one full pipe with several at least 100 of that kind of device, we can get many one, and you can use it for different application. I don't know exactly what instrument they will run or what we will run right now, but what is good feeling is that we are actually wasting 60 to 70% heat, okay, which is free to you, and then you generate electricity and do whatever you want from that electricity.
Right.
Thank you, sir.
Right.
Thank you.
So yeah, so Kanishka, what about the this as you said from 10 gram to some 200 gram? So the, how, and the price wise, this material doesn't cost much.
Yeah, so price wise, this is similar to bismuth telluride based module. What you have, so I have silver and antimony, and silver is actually cheaper than tellurium. You know, tellurium is the most costly element in this compound. So tellurium is same for bismuth telluride. So I have a similar price thing, and so for this compound. So price wise, we are not losing much, but we are gaining with efficiency.
Yeah, excellent.
But the problem is that, like last 4-5 years, I have faced a huge challenge to going to the scale up and multiple like device making. So at the end, it worked because I found a good collaborator.
Right. No, this is something you need some collaborator who are expertise packaging and all. Definitely.
Yeah, so he's a metallurgical engineer. So actually, he's more interested to do that kind of job. Right. And so we are more interested in understanding his localization. So that's the problem. Yeah. So
okay, I have one basic fundamental question side.
Sure.
So yeah, you said that there are small order structure in a sort of like a disorder environment. Of course, they are not. These are small order structure, but they are not aligned.
Right.
But if I think of something like a Moire superlattice, for example.
Right.
Will not also that will do a similar role, because if I have Moire superlattice, my Biswas now becomes smaller because I have a order structure, in different size now, which is much bigger than lattice constant.
Right.
And once I Biswas is squeezed, my phonon will be hybridized and all. So I have more phonon scattering, 3 phonon and all this process.
Right.
So so I don't know. Does it help also to reduce?
It should help. Like see the Moire patterns as the periodicity pattern has a similar size to the phonon mean paper. It will also scatter huge amount of phonon. So, but the periodicity should be in the nanometer basically.
Right.
But if it is in micron, then it may not help.
Yeah. So this phonon mean paper, you are saying that's depending at some particular temperature.
So material to material. But generally, this kind of thermoelectric, high performance thermoelectric material, like say lead telluride, bismuth telluride, tin telluride, germanium telluride, or selenides, or sputterolides, this kind of material phonon mean paper lies around, which actually the important phonon, the acoustic phonon, 1 to 20 nanometer, basically.
1 to 20 nanometer. Right.
So that's why, like, this is a game of nanoscience basically. So how to scatter the phonons.
Exactly. Very interesting. So this Mercury, the latest one, what you said that right now you are doing, and you have a better structure of this order one.
Yeah.
So this the jet is higher than your science paper, or they are very similar?
Jet is similar. But I didn't show a data. Actually, I have a data which is close to 3 now. Jet is, which is higher than science paper. So when we created more and more difference. So
excellent, very good. So there is one question, from Dr. Kavita, for these materials are in industrial scale or commercial purpose.
See, like we cannot make an industrial scale in my lab. Okay, so we can actually we made up to 150 gram. Okay, so then we collaborated with Tata Steel and ARCI. So they scaled up to say around 200 250 gram. So now what they are doing, they are giving it to a third party, which is placed in IIT Chennai research park. So they promise that they can make up to kilogram or easily. So that's what, like, I have to give him the know-how, but we have a patent protected everything. So.
Okay, I think. Okay, there are no more questions. Very interesting, Kanishka. Very interesting. You have a playground using the periodic table now, basically, right? And how robust this material, like with time, does it degrade or?
So I'll see. We have some data is there, I guess. Yeah. So you see this is the cycle, 3-cycle data. The jet is almost stable. Okay. Yeah. So, and this is the cycle 1, cycle 2, cycle 3. So these data are there. Yeah. So we have tested everything, like, because see, like this is more and more, this kind of question came more and more when we started working with industry.
Yeah, exactly.
Yeah, so
this kind of questions are important, not for
because they ask us to prepare 10 batches and show similar jet in the error bar. We have done it actually. So,
absolutely. Okay, is there any question? So there is one more comment. Professor Anand Kulkarni, he is asking which metal oxide produces most thermoelectric power.
Okay, so this is an interesting question. So actually metal oxides are not very good for thermoelectrics, because I'll go to this diagram, what I said slowly. So see, metal oxides basically are generally insulators with the band gaps in the range of say 3 to 4 electron volt. So once you have a very high band gap, you cannot get metal-like conductivity so easily. And then oxide, you are working with a lighter element, right? Your thermal conductivity will fall in the range of 40 to 50 or 30 to 40 watt per meter Kelvin. Wherever I am starting in this telluride from 2-3 watt per meter Kelvin, and we are bringing down to around 0.2 to 0.3 watt per meter Kelvin. So both ways, oxides are no good, but still, if you wanted to work in oxide, pyrochlores are good, which are having a complex structure. So once you have a complex unit cell or bigger unit cell, it will have some intrinsic phonon scattering. So we can start with around 8 to 9 watt per meter Kelvin. So pyrochlore oxides probably be a good idea to work with if you wanted to work in oxide.
Fantastic. Okay, if there are no questions, let's thank Professor Biswas once again for a wonderful and excellent talk. And we wish all the best for your, these prototype devices and industrial scale application in future. And with this, okay, so the
one more question is there.
Yeah, Professor Kulkarni, please, you can unmute and you can directly ask.
Sir, whether can I use polymer metal oxide nanocomposite for thermoelectric power?
Which one?
Sir, polymer metal oxide.
Why you want to use polymer?
Yeah, sir.
Now, why you want polymer?
For point of electrical conductivity.
Polymer will not increase electrical conductivity of oxide.
Sir, the composite of metal oxide, sir, both.
I got it. But the polymer may not enhance the electrical conductivity of oxide, because polymer is organic material. No, it will have much lesser conductivity.
Yeah, sir.
Yeah. So if you wanted to work with polymer, mix polymer with bismuth telluride. That will be better.
Polyaniline, sir. I worked on polyaniline.
Yeah. So mix polyaniline with bismuth telluride. That will be better.
Yeah, polymer and which one, sir?
Bismuth telluride. Mix it with bismuth.
Yeah. Thank you, sir. Thank you.
Yeah, thank you.
Thank you very much.
Okay, good. So so Venkatesh, you can close the session.
Thank you very much.
Venkatesh, you are muted.
Distinguished invitees, ladies and gentlemen, good evening to everyone. At the outset, it gives me immense pleasure to propose vote of thanks for all the participants of this talk, and we wish to express our sincere thanks to Professor Kanishka Biswas, Professor at JNCSR, for his very interesting and excellent talk. Thank you very much, sir. Our special thanks to Professor Anindya Das, convener of Bengaluru, India monthly webinar series 22-23, and Professor Department of Physics for his valuable guidance in planning the Bengaluru, India Nano Talks. I also thank all the distinguished invitees and participants of this program. We look forward to your continued support and participation in the Bengaluru, India Nano monthly webinar series. Thank you one and all again. Thank you, sir.
Okay, thank you all. Yeah, bye Kanishka, bye everyone, bye Venkatesh.
Thank you.
Thank you all.